You've heard of three dimensions: length, width, and height. Maybe even four if you count time. But what if there are more? What if hidden dimensions surround us at every moment, threading through the very fabric of reality? Yet we remain completely blind to their existence? Where are all the hidden dimensions? And why has no one ever seen them? This isn't science fiction. This is one of the most profound questions haunting modern physics. A mystery that could reshape everything we think we know about the universe. Right now, as you read these words, you might be sitting just millimeters away from entire worlds, dimensions folded so tightly into the structure of space that they exist beyond perception, operating according to rules we're only beginning to glimpse. The secret structure of the universe may be far stranger and more complex than our three-dimensional minds can fully comprehend. To understand why physicists believe these extra dimensions must exist, we need to step back and examine one of the most elegant and troubling problems in modern science. It begins with a simple observation that should terrify anyone who thinks deeply about it. The forces that govern our universe don't make sense, not in the way we experience them anyway. Consider gravity. Right now, Earth's gravitational field is holding you in your chair, keeping the atmosphere from drifting into space, and maintaining the delicate orbital dance that keeps our planet circling the sun. Gravity seems incredibly powerful. It shapes galaxies, bends light, and can crush matter into black holes. Yet compared to the other fundamental forces, gravity is absurdly, almost impossibly weak. How weak? If you've ever picked up a paperclip with a small magnet, you've witnessed electromagnetic force overpowering the gravitational pull of an entire planet. The magnet in your hand generates a force stronger than the combined gravitational attraction of Earth's 6 trillion kilograms of mass. This isn't just a minor discrepancy, it's a difference so vast. It suggests something fundamental about reality is hidden from us. The numbers are staggering. Electromagnetic force is roughly a trillion times stronger than gravity. In the world of physics, where elegant equations and beautiful symmetries reign supreme, this kind of disparity is like finding a single instrument playing pianissimo in an orchestra where everything else is fortissimo. It demands explanation. This puzzle, known as the hierarchy problem, has driven physicists to propose increasingly exotic solutions. And the most compelling answer they've found is this: gravity isn't actually weak. It just appears weak to us, because most of its strength is bleeding away into dimensions we cannot see. Imagine you're standing in a vast, empty field, shouting at the top of your lungs. To someone standing next to you, your voice seems loud and clear. But what if, unbeknownst to both of you, there were invisible tunnels carved throughout the ground, beneath your feet? Passages that carried most of your voice's energy, away into hidden chambers underground? The person next to you would hear only a faint whisper of your actual vocal power. Most of your voice would be lost in dimensions they couldn't perceive. This is the essence of how hidden dimensions might work. Gravity, according to these theories, broadcasts its influence across all dimensions of space. In our familiar three-dimensional world, we feel only the tiny fraction of gravitational force that remains after most of it has dispersed into the hidden dimensions that permeate reality. The mathematical framework for this idea emerged from one of the most ambitious intellectual projects in human history: string theory. Unlike the point-like particles of conventional physics, String theory proposes that the fundamental building blocks of reality are tiny, vibrating strings of energy. These strings exist not in our familiar 3 dimensions of space, but in a reality with as many as 11 dimensions total. Why 11? The mathematics of string theory simply refuses to work in fewer dimensions. When physicists first developed the equations that describe these vibrating strings, they discovered something remarkable and disturbing. The math only produces consistent, stable solutions when calculated in specific numbers of dimensions, and those numbers are far higher than the 3 spatial dimensions we experience. It's as if the universe itself is demanding more room to operate than we can provide. The equations describing the deepest level of reality require a stage with 10 or 11 dimensions. Yet we find ourselves apparently trapped in a cramped 3-dimensional theater, watching shadows of a much grander performance. But here's where the story becomes even stranger. If these extra dimensions exist, they must be hidden from us in a way that's both subtle and total. We've built particle accelerators that smash atoms together at energies approaching those present at the birth of the universe. We've detected gravitational waves from colliding black holes billions of light years away. We've measured the cosmic microwave background radiation with exquisite precision, seeing the universe as it existed when it was only 380,000 years old. Yet none of these incredibly sensitive instruments has given us direct evidence of extra dimensions. This leads to one of 2 possibilities, both mind-bending in their implications. Either these dimensions don't exist, and we need to find some other explanation. For gravity's weakness and the mathematical demands of string theory, or they do exist, but are hidden from us through mechanisms so elegant and complete that we've never detected them despite decades of searching. The leading explanation for how dimensions could hide involves a concept called compactification. Imagine an ant walking along what appears to be a thin wire. To the ant, the wire seems one-dimensional. It can move forward or backward, but that's all. However, if you examine the wire under a microscope, you might discover it's actually a thin tube. The ant could, in principle, also move around the circumference of the tube. But this dimension is so small compared to the ant's size that it might never notice it exists. Now scale this concept down to the fundamental structure of space itself. What if every point in our familiar 3-dimensional space is actually a tiny, complex geometric shape, with additional dimensions curled up so small that even our most powerful instruments cannot detect them? These compactified dimensions would exist at every location in our universe, but would be rolled up so tightly, perhaps at the scale of the Planck length, which is about 10 yans 35 meters, that they remain invisible to us. To put this in perspective, if an atom were scaled up to the size of our solar system, the Planck length would still be smaller than a tree. These dimensions aren't just small, they exist at a scale so minute that they challenge our very conception of what size even means. But compactification raises its own profound questions. If these dimensions are curled up at every point in space, what determines their shape? The geometry of these hidden dimensions would profoundly influence the physics we observe in our 3-dimensional world. Different shapes would produce different particles, different forces, different physical constants. The fact that our universe has the specific properties it does, the particular masses of electrons and quarks, the precise strengths of the fundamental forces, the exact value of the cosmological constant, might be determined by the intricate geometry of dimensions we cannot see. This leads to a staggering possibility. There might be countless ways to fold up these extra dimensions, each producing a universe with different physical laws. We might inhabit just one bubble in an infinite multiverse, where each bubble represents a different way of compactifying the hidden dimensions. In some bubbles, electrons might be heavier, making atoms impossible to form. In others, the strong nuclear force might be weaker, preventing the formation of complex nuclei. We exist in the particular bubble where the dimensional geometry happened to produce physics compatible with the evolution of complexity, consciousness, and life. Yet even this elegant explanation faces challenges. If extra dimensions are compactified at the Planck scale, they should produce observable effects. In high-energy physics experiments, particles created in accelerators should occasionally disappear into these hidden dimensions, or exotic particles from the higher dimensional world should occasionally appear in our detectors. The fact that we haven't seen such effects places strict limits on how these dimensions could be structured. This has led some physicists to propose even more exotic possibilities. What if the extra dimensions aren't compactified at all, but are, instead, separated from us by some other mechanism? What if we're trapped on a three-dimensional brane, a higher-dimensional analog of a two-dimensional membrane, floating in a space with additional large dimensions? In this scenario, the big particles that make up ordinary matter might be confined to our brain, while gravity, which operates through the curvature of spacetime itself, could propagate freely through all dimensions. This Brainworld model offers a different solution to gravity's weakness. If gravity can spread out into large extra dimensions, while other forces remain trapped on our three-dimensional brane, then gravity would naturally appear weaker to us, even if it's actually comparable in strength to the other forces in the full higher dimensional space. The implications are staggering. If large extra dimensions exist, we might be living in a shadow of a much vaster reality. Parallel branes might float nearby in the higher dimensional space, harboring their own versions of matter and energy, their own physics, perhaps even their own forms of life. These parallel worlds could exist just millimeters away from us in the extra dimensions, yet be completely inaccessible because the particles that compose our bodies are forever confined to our three-dimensional slice of reality. Some versions of Brainworld theory suggest that these parallel branes might occasionally collide, producing Big Bang-like events that create new universes. The cosmic microwave background radiation that we observe, the afterglow of our own Big Bang, might actually be the echo of such a collision, frozen in time as a testament to the higher dimensional catastrophe that gave birth to our world. But if these extra dimensions exist, why haven't we found them? The search has consumed enormous resources and generated increasingly sophisticated experiments. Physicists have looked for deviations from Newton's inverse square law of gravity at microscopic scales, reasoning that if large extra dimensions exist, gravity should behave differently at distances comparable to the size of those dimensions. They've searched for missing energy in particle collisions, hoping to catch particles disappearing into hidden dimensions. They've studied the precise details of how space and time behave near black holes, looking for signatures of higher dimensional physics. Each experiment has pushed the boundaries of what's possible, yet the extra dimensions remain elusive. Either they're hidden more cleverly than we imagine, or they don't exist at all. Both possibilities are deeply unsettling for different reasons. If extra dimensions don't exist, then we're left with the original hierarchy problem. Why is gravity so much weaker than the other forces? More troubling, it would mean that string theory, our most promising candidate for a theory of quantum gravity, might be describing a reality that has no connection to our own. The mathematical beauty and elegance that initially attracted physicists to string theory could be nothing more than an elaborate mirage, a consistent but irrelevant mathematical structure that tells us nothing about the actual universe we inhabit. On the other hand, if extra dimensions do exist but remain hidden through mechanisms we haven't yet understood, it suggests that reality is far stranger and more complex than we've imagined. We might be like ancient philosophers trying to understand the nature of matter without knowledge of atoms, or astronomers before Galileo trying to comprehend the cosmos without telescopes. The true structure of reality might be so far beyond our current conceptual frameworks that we lack even the vocabulary to properly describe it. The search for hidden dimensions has also led to profound questions about the nature of space and time themselves. In our everyday experience, space seems like a passive stage upon which the drama of physics unfolds. But general relativity revealed that space and time are dynamic, capable of curving and stretching in response to matter and energy. The possibility of extra dimensions suggests that this dynamism might extend into realms we cannot perceive. What would it mean for space itself to have hidden structure? Every point around you, the space between your fingers, the gap between atoms in the air you breathe, the vacuum between Earth and the stars, might be honeycombed with invisible tunnels and chambers, folded origami-like into configurations that exist beyond the reach of our senses. The apparently empty space that surrounds you might be teeming with activity in dimensions you cannot access. This possibility has captured imaginations far beyond the physics community. Science fiction writers have long explored the idea of hidden dimensions as gateways to other worlds, shortcuts across vast distances, or reservoirs of exotic energy. While the actual physics of extra dimensions is likely to be far more subtle and constrained than these fictional portrayals suggest, the underlying concept that reality extends beyond what we can perceive resonates with something deep in human nature. Perhaps it's the same impulse that drives us to wonder what lies beyond the horizon, or what secrets might be hidden in the depths of the ocean. The possibility of hidden dimensions appeals to our sense that the universe is larger and stranger than it appears, that there are always new frontiers waiting to be discovered. Yet the search for these dimensions also highlights the limitations of human perception and intuition. We evolved to navigate a three-dimensional world at human scales, detecting threats and opportunities, finding food and shelter, recognizing faces, and interpreting social cues. Nothing in our evolutionary history prepared us to think about 11-dimensional space or to visualize the geometry of compactified dimensions. This creates a profound challenge for physics education and public understanding of science. How do you explain concepts that exist beyond the boundaries of human experience? How do you build intuition for phenomena that operate according to rules our brains never evolved to comprehend? The mathematics provides a bridge across this conceptual gap, offering a language that can describe realities our senses cannot directly access. But mathematics is itself a human creation, shaped by the particular way our minds process information and recognize patterns. There's no guarantee that our mathematical frameworks are adequate to capture the full richness of a higher dimensional reality. This leads to one of the most unsettling questions in modern physics. What if extra dimensions exist but are fundamentally incomprehensible to human minds? What if the true nature of reality operates according to principles so alien to our three-dimensional experience that we can never fully understand them, only create approximate mathematical models that capture small aspects of a much grander truth? The search for hidden dimensions thus becomes more than just a technical problem in theoretical physics. It becomes a meditation on the limits of human knowledge, the relationship between mathematical models and physical reality, and the possibility that the universe might be far stranger than we can imagine. As we stand at this conceptual precipice, peering into the mathematical abyss of higher dimensional space, we're confronted with the humbling possibility that everything we think we know about reality might be just the shadow cast by a much larger and more complex truth. The question isn't just where the hidden dimensions are, but whether we're capable of finding them, and what it might mean for our understanding of existence itself if we do. The story of hidden dimensions begins not with exotic mathematics or particle accelerators, but with a simple, almost childlike question that has haunted physicists for over a century. Why does the universe work the way it does? Why are there exactly 4 fundamental forces? Why do particles have the specific masses they do? Why does space-time behave according to Einstein's equations rather than some other set of rules? The deeper physicists have probed these questions, the more they've become convinced that our familiar three-dimensional reality is merely the surface of something far more profound and complex. To understand how we arrived at the notion of hidden dimensions, we must first appreciate the profound crisis that modern physics faced at the dawn of the 20th century. By the 1890s, many scientists believed that physics was essentially complete. Newton's laws explained motion. Maxwell's equations described electromagnetism, and thermodynamics governed heat and energy. The universe seemed to operate like a vast, predictable clockwork mechanism. Yet within a few decades, this comfortable worldview would be shattered by discoveries that revealed reality to be far stranger than anyone had imagined. The first crack. In this classical facade came with Max Planck's reluctant introduction of quantum theory in 1900. While trying to solve a seemingly mundane problem about how objects emit light when heated, Planck discovered that energy comes in discrete packets, or quanta. This finding was so contrary to classical physics that Planck himself initially resisted its implications. But the mathematics was undeniable. At the smallest scales, nature operates according to rules that bear no resemblance to our everyday experience. Einstein's special and general theories of relativity dealt the next devastating blow to classical physics. Space and time, which had seemed absolute and unchanging since Newton, were revealed to be relative and dynamic. Even more shocking, Einstein showed that space-time itself could be curved and warped by matter and energy. The universe wasn't a static stage upon which physics unfolded. It was a participant in the cosmic drama, bending and stretching in response to the actors upon it. These revolutionary discoveries created new problems, even as they solved old ones. Quantum mechanics and general relativity, despite their individual successes, proved to be fundamentally incompatible. Quantum mechanics describes the behavior of the very small with extraordinary precision, while general relativity explains gravity and the large-scale structure of the universe with equal accuracy. Yet when physicists try to combine these theories, as they must when studying phenomena like black holes or the first moments after the Big Bang, the mathematics breaks down completely. This incompatibility isn't merely a technical inconvenience. It represents a profound gap in our understanding of reality. At the deepest level, we don't know how the universe actually works. We have two partial descriptions that each capture important aspects of nature, but we lack a unified framework that can encompass both the quantum world and the gravitational realm. String theory emerged as the most promising candidate for bridging this gap. Developed initially in the late 1960s and early 1970s, string theory proposes that the fundamental constituents of reality aren't point-like particles, but tiny, vibrating strings of energy. These strings are unimaginably small. If an atom were scaled up to the size of the solar system, a string would still be smaller than a tree. Yet according to the theory, all the particles and forces in the universe arise from different patterns of vibration in these microscopic strings. The elegance of this idea is breathtaking. Just as a violin string can produce different musical notes depending on how it vibrates, the fundamental strings of string theory can produce different particles, electrons, quarks, photons, gravitons, depending on their vibrational patterns. In this view, the entire symphony of physics, from the smallest subatomic particles to the largest cosmic structures, emerges from the harmonious vibrations of these tiny strings. But string theory came with a shocking requirement. It only works consistently in spacetime with more than 4 dimensions. The mathematics of string theory simply refuses to produce stable, sensible solutions unless it operates in either 10 or 11 total dimensions. This wasn't a choice made by physicists, it was a demand made by the mathematics itself, as if the deepest laws of nature were insisting on more room to operate than our familiar world provides. What are hidden dimensions in physics? And if they exist, where are they hiding in the fabric of space-time? According to string theory, the universe may hold compactified dimensions, curled so tightly we can never see them. These extra dimensions don't exist somewhere else. They exist everywhere, at every point in the space around you. They're woven into the very fabric of reality, yet remain invisible because they're curled up at scales so small that even our most powerful instruments cannot detect them. To visualize this concept, imagine looking at a garden hose from a great distance. The hose appears to be a one-dimensional line stretching across your yard, but as you move closer, you realize that the hose actually has width. It extends into a second dimension that was invisible from far away. Now, imagine moving even closer and discovering that the surface of the hose has a complex texture, with tiny ridges and valleys that create additional spatial structure invisible from any reasonable distance. String theory suggests that every point in our familiar three-dimensional space is like that garden hose viewed from far away. What appears to be a simple point actually has additional dimensional structure, complex geometric shapes called Calabi-Yau manifolds that exist at scales so small they remain hidden from all direct observation. These compactified, curled-up spaces aren't empty voids, but intricate geometric landscapes with their own topology, their own rules, their own hidden physics. The discovery of these mathematical requirements forced physicists to confront a disturbing possibility. We might be fundamentally limited in our ability to perceive reality. If the universe actually has 10 or 11 dimensions, but we can only access 3 of space and 1 of time, then most of existence remains forever beyond our direct experience. We're like inhabitants of a 2-dimensional world trying to understand 3-dimensional objects. We can see their shadows and cross-sections, but never the full reality. This limitation becomes even more profound when we consider that the shape and size of the hidden dimensions would determine many of the properties we observe in our 3-dimensional world. The masses of particles, the strengths of forces, even the number of distinct particle types, all of these might be consequences of the particular way the extra dimensions are folded up at every point in space. M theory, which emerged in the EO 1990s as a more complete version of string theory, deepened these mysteries while providing new insights. M theory suggests that our universe might be a 3-dimensional brane, a higher dimensional analog of a 2-dimensional membrane floating in an 11-dimensional space. In this picture, the particles that make up ordinary matter are confined to our brain, like ants crawling on the surface of a balloon. Meanwhile, gravity, which operates through the curvature of space-time itself, can propagate freely through all 11 dimensions. This Brainworld scenario offers a potential explanation for one of physics' most perplexing puzzles: why gravity is so much weaker than the other fundamental forces. If gravity can spread out into the extra dimensions while other forces remain trapped on our 3-dimensional brane, then gravity would naturally appear weaker to us, even if it's actually comparable in strength to the other forces in the full 11-dimensional space. But M-theory also raises mind-bending possibilities about the nature of reality itself. If our universe is indeed a brane floating in higher dimensional space, there could be other branes nearby, parallel universes with their own matter, their own physics, perhaps even their own forms of life. These parallel worlds could exist, just millimeters away from us in the extra dimensions, yet be completely inaccessible because the particles that compose our bodies are forever confined to our three-dimensional slice of reality. Can we detect hidden dimensions? The question has driven decades of experimental searches, each more sophisticated than the last. Physicists have looked for violations of Newton's inverse square law at microscopic distances, reasoning that if large extra dimensions exist, gravity should behave differently at scales comparable to the size of those dimensions. They've searched for missing energy in particle collisions, hoping to catch particles disappearing into hidden dimensions. They've studied the cosmic microwave background radiation with exquisite precision, looking for signatures of higher dimensional physics imprinted on the afterglow of the Big Bang. The Large Hadron Collider at CERN represents the current pinnacle of this search. This massive machine accelerates protons to nearly the speed of light and smashes them together at energies approaching those present in the first moments after the Big Bang. If extra dimensions exist and are accessible at these energy scales, the collisions should produce clear signatures, particles disappearing into the hidden dimensions, exotic particles emerging from higher dimensional space, or gravitational effects that don't follow the familiar three-dimensional pattern. Yet, despite decades of searching with increasingly powerful instruments, the extra dimensions remain stubbornly hidden. Each negative result places new constraints on how these dimensions could be structured, forcing theorists to propose ever more exotic mechanisms for keeping them concealed from observation. The mathematics behind these hidden dimensions is as beautiful as it is bewildering. The Calabi-Yau manifolds that describe the shape of compactified dimensions are geometric objects of extraordinary complexity and elegance. Named after mathematicians Eugenio Calabi and Xing-Tung Yau, these shapes exist in 6 dimensions and possess special properties that make them suitable for the extra dimensions required by string theory. To appreciate the intricacy of these mathematical structures, consider that a typical Calabi-Yau manifold might have hundreds of holes, topological, features that affect how strings can wrap around the manifold and vibrate. Each different way of threading strings through these holes corresponds to different particles in our three-dimensional world. The particular Calabi-Yau shape that describes our universe would determine not just what particles exist, but their masses, charges, and interaction strengths. This leads to one of the most profound questions in modern physics. How many hidden dimensions exist in the universe, and why do they have the particular shape they do? The mathematics of string theory allows for an enormous number of possible Calabi-Yau manifolds. Some estimates suggest there could be as many as 10,500 different ways to compactify the extra dimensions. Each would correspond to a universe with different physical laws, different particles, different forces. We seem to live in the particular universe where the dimensional geometry happened to produce physics compatible with the formation of atoms, stars, planets, and ultimately life itself. But this raises the unsettling possibility that we're just one bubble in a vast multiverse, where each bubble represents a different way of folding up the hidden dimensions. In most bubbles, the physics might be sterile, unable to form complex structures or support the emergence of consciousness. The landscape problem, as this proliferation of possibilities is known, represents one of the deepest challenges facing string theory. If the theory allows for 10,500 different universes, how can it make testable predictions about our particular universe? How can we determine which of these countless possibilities corresponds to reality? Some physicists have embraced this multiplicity, arguing that it actually explains why our universe has the particular properties it does. In a multiverse containing every possible way of compactifying the extra dimensions, it's not surprising that we find ourselves in one of the rare bubbles where the physics allows for complexity and life. This anthropic reasoning suggests that the apparent fine-tuning of our universe's physical constants isn't evidence of design, but simply a selection effect. We observe a life-friendly universe because we couldn't exist in any other kind. Yet, this anthropic explanation troubles many physicists. Science has traditionally progressed by finding simple, elegant explanations for complex phenomena. The idea that we live in a random bubble, in an infinite multiverse, seems to abandon this quest for understanding in favor of a kind of cosmic lottery ticket. It suggests that many of the deepest questions about our universe, why the electron has the mass it does, why the cosmological constant has its observed value, might not have answers in any meaningful sense. The mathematical sophistication required to work with higher dimensional geometry has pushed physics into increasingly abstract territory. Physicists routinely manipulate equations describing 11-dimensional spaces, calculate the properties of 6-dimensional Calabi-Yau manifolds, and study the dynamics of strings moving through spaces that exist beyond human visualization. This mathematical abstraction has created a growing gap between theoretical physics and experimental reality. While experimentalists search for concrete evidence of extra dimensions, theorists work with mathematical structures so complex and abstract that their connection to physical reality becomes increasingly tenuous. Some critics argue that string theory has become more mathematics than physics, a beautiful and consistent mathematical framework that may have no connection to the actual universe we inhabit. The challenge of visualization adds another layer of difficulty to understanding hidden dimensions. Our brains evolved to navigate three-dimensional space, and we have no direct intuitive access to higher dimensional geometry. Physicists have developed various tricks for visualizing these spaces: cross-sections, projections, analogies, but these are all approximations that capture only limited aspects of the full reality. Consider the challenge of truly understanding what a Calabi-Yau manifold looks like. These 6-dimensional shapes exist in a space that no human mind can directly visualize. We can create 2-dimensional cross-sections that show us how the manifold appears when sliced in various ways, or we can project its shadow into 3-dimensional space, but we can never see the full object as it actually exists. This limitation extends beyond mere visualization to conceptual understanding. How do you develop physical intuition for phenomena that operate in dimensions you cannot access? How do you distinguish between mathematical structures that correspond to physical reality and those that are merely consistent abstractions with no connection to the actual universe? The history of physics suggests that mathematical consistency often points toward physical truth. The equations of general relativity predicted the existence of black holes decades before they were observed. Quantum mechanics anticipated the I-way, existence of antimatter, quantum tunneling, and other phenomena that seemed impossible from a classical perspective. The mathematical structure of these theories revealed aspects of reality that no amount of pure experimentation could have uncovered. String theory and M-theory follow in this tradition, using mathematical consistency as a guide toward deeper truth. The fact that these theories require extra dimensions isn't an arbitrary choice made by physicists, it's a demand made by the mathematics itself. The equations simply don't work in fewer dimensions, just as the equations of electromagnetism don't work without the concept of fields, or the equations of quantum mechanics don't work without probability amplitudes. Yet the history of physics also contains examples of beautiful mathematical theories that turned out to have no connection to physical reality. The crystal spheres that ancient astronomers used to explain planetary motion were mathematically sophisticated and observationally accurate, but they described a geocentric universe that doesn't exist. The luminiferous ether that 19th-century physicists believed filled all space was a mathematically consistent concept that explained many optical phenomena, but it turned out to be completely fictitious. This raises the uncomfortable possibility that string theory and its extra dimensions might be following the same path. Elaborate mathematical constructions that capture some aspects of nature but miss the deeper truth. The beauty and elegance that originally attracted physicists to these theories might be leading them away from reality rather than toward it. The experimental situation adds urgency to these concerns. Despite decades of increasingly sophisticated searches, we have found no direct evidence for extra dimensions. The Large Hadron Collider, which many hoped would reveal signs of higher dimensional physics, has instead confirmed the predictions of the Standard Model of particle physics, a theory that works perfectly well in our familiar four-dimensional spacetime. This doesn't necessarily mean that extra dimensions don't exist. They might be hidden more cleverly than we've imagined, compactified at scales so small or accessible only at energies so high that they remain beyond our current experimental reach. The history of physics is filled with phenomena that remained hidden for decades or centuries before the right experiments or instruments revealed them. But it does mean that the case for extra dimensions rests primarily on theoretical, rather than experimental grounds. We believe they exist because our best theories of quantum gravity seem to require them, not because we've observed them directly. This situation makes many physicists uncomfortable, as it represents a departure from the empirical foundation that has driven scientific progress for centuries. The question of hidden dimensions also intersects with some of the deepest philosophical questions about the nature of reality and knowledge. If extra dimensions exist, but remain forever beyond our ability to observe them directly, what does it mean to say they're real? How do we distinguish between mathematical structures that correspond to physical reality and those that are merely consistent abstractions? These questions echo ancient philosophical debates about the relationship between the world we perceive and the world that actually exists. Plato's allegory of the cave suggested that we might be like prisoners chained in darkness, seeing only shadows of a higher reality. The possibility of hidden dimensions gives this ancient metaphor a startling modern relevance. We might indeed be confined to a lower dimensional shadow of a much grander and more complex reality. The implications extend beyond physics to our understanding of human knowledge and limitation. If the universe actually has 11 dimensions, but we can only perceive 4, then most of existence remains forever beyond our direct experience. We're fundamentally limited beings trying to understand an unlimited reality, using three-dimensional branes to comprehend 11-dimensional spaces. Yet perhaps this limitation is also what makes the search for hidden dimensions so profound and meaningful. The fact that we can even conceive of realities beyond our direct perception, that we can construct mathematical frameworks to describe spaces we cannot visualize, represents one of the most remarkable achievements of human consciousness. Through mathematics and theoretical physics, we've found ways to transcend the biological limitations of our three-dimensional experience and explore realms that exist beyond the boundaries of direct observation. The search for hidden dimensions thus becomes more than just a technical problem in theoretical physics. It becomes a meditation on the relationship between mind and reality, between mathematical truth and physical existence, between the world we experience and the world that actually is. Whether or not extra dimensions exist in physical reality, they've already transformed our understanding of what it means to search for truth in a universe that might be far stranger and more wonderful than our limited perceptions can directly reveal. As we stand at this conceptual frontier, peering into mathematical spaces that extend beyond human visualization, we're confronted with the humbling possibility that reality extends far beyond the boundaries of human experience. The hidden dimensions, whether they exist in physical space or only in the abstract realm of mathematical possibility, remind us that the universe may be far grander, more complex, and more mysterious than we can ever fully comprehend. The mathematical universe reveals its secrets reluctantly, like an ancient manuscript written in a language that barely translates into human understanding. When physicists first began exploring the possibility of hidden dimensions, they weren't searching for exotic realms or parallel universes. They were simply trying to solve an embarrassing problem that had plagued physics for decades. The problem was gravity, and its solution would lead them into territories so strange that even science fiction writers had barely imagined them. The story begins in 1919, just 4 years after Einstein published his general theory of relativity. A relatively unknown German mathematician named Theodor Kaluza wrote to Einstein with a remarkable proposal. What if, Kaluza suggested, there were actually 5 dimensions of spacetime instead of 4? What if gravity and electromagnetism, the only fundamental forces known at the time, were actually different aspects of the same phenomenon, unified in this higher dimensional space? Einstein was initially skeptical, but Kaluza's mathematics were compelling. By adding a 5th dimension to spacetime and then compactifying it, rolling it up so tightly that it remained invisible at everyday scales, Kaluza showed that Einstein's equations of general relativity would naturally produce both gravitational and electromagnetic fields in our familiar 4-dimensional world. It was an elegant idea. Forces that seemed completely different in 4 dimensions were revealed to be unified when viewed from the perspective of 5-dimensional spacetime. The Swedish physicist Oscar Klein later refined Kaluza's idea, developing what became known as Kaluza-Klein theory. Klein showed that the 5th dimension would have to be curled up into a tiny circle at every point in ordinary space, with a circumference on the order of the Planck length, about 10^35 35 meters. This was so small that the dimension would remain completely hidden from any conceivable experiment. Yet its presence would manifest itself through the electromagnetic force we observe in our 3-dimensional world. Kaluza-Klein theory was mathematically beautiful, but it had a serious problem. It predicted the existence of particles that didn't seem to exist in nature. Moreover, as physicists discovered more fundamental forces, the strong nuclear force that holds atomic nuclei together, and the weak nuclear force responsible for certain types of radioactive decay, the simple 5-dimensional framework of Kaluza-Klein theory proved inadequate to describe the full complexity of physical reality. Yet the basic insight of Kaluza-Klein theory, that forces apparently distinct in our low-dimensional world might be unified in a higher dimensional space, would prove prophetic. As physicists developed increasingly sophisticated theories to describe the fundamental structure of reality, they found themselves repeatedly drawn back to the idea that extra dimensions might hold the key to understanding the deepest mysteries of the universe. The next major breakthrough came with the development of string theory in the late 1960s and early 1970s. Originally conceived as a theory of the strong nuclear force, string theory proposed that the fundamental constituents of reality weren't point-like particles, but tiny, vibrating strings of energy. These strings were unimaginably small. If an atom were scaled up to the size of the solar system, a string would still be smaller than a tree. Yet according to the theory, all the particles and forces in the universe arose from different patterns of vibration in these microscopic strings. String theory came with a shocking requirement that echoed the earlier insights of Kaluza and Klein. It only worked consistently in space-time with more than 4 dimensions. But where Kaluza-Klein theory required just one extra dimension, string theory demanded 6 additional spatial dimensions for a total of 9 spatial dimensions plus 1 dimension of time. The mathematics of string theory simply refused to produce stable, sensible solutions unless it operated in this 10-dimensional space-time. How many hidden dimensions does string theory predict? And what lies inside those folded layers of reality? The answer depends on which version of string theory you consider. But all consistent formulations require additional dimensions beyond the 4 we experience. These quantum dimensions aren't separate from our familiar space. They exist at every point in the universe, woven into the very fabric of reality itself. To understand how 6 extra dimensions could exist without being observed, physicists developed increasingly sophisticated models of compactification. Unlike the simple circular dimension of Kaluza-Klein theory, the 6 extra dimensions of string theory had to be compactified in much more complex ways. The spaces that emerged from these calculations were geometric objects of extraordinary intricacy. 6-dimensional shapes with hundreds of holes, twists, and topological features that would make even the most complex origami look simple by comparison. These compactified spaces, known as Calabi-Yau manifolds, became the focus of intense mathematical study. Named after the mathematicians Eugenio Calabi and Xing-Tung Yau, these 6-dimensional shapes possess special geometric properties that make them suitable for the extra dimensions required by string theory. They must satisfy complex mathematical constraints. They must be Ricci flat, meaning their curvature vanishes in a particular sense, and they must preserve a certain amount of supersymmetry, a hypothetical symmetry between particles and forces. The mathematical description of Calabi-Yau manifolds reads like poetry, written in the language of advanced geometry. These spaces can have moduli, parameters that describe their size and shape, that can vary from point to point in our familiar 3-dimensional space. They can have different numbers of holes, technically called cycles, which determine how strings can wrap around the manifold and vibrate. Each different way of threading strings through these cycles corresponds to different particles in our 3-dimensional world. But the beauty of Calabi-Yau manifolds comes with a troubling consequence. There are far too many of them. Conservative estimates suggest there might be 10 to 500 different ways to compactify the 6 extra dimensions of string theory, each corresponding to a universe with different physical laws. This vast landscape of possibilities, known as the string theory landscape, represents one of the most serious challenges facing the theory. If string theory allows for $10,500 different universes, how can it make testable predictions about our particular universe? This question became even more pressing with the development of M-theory in the 1990s, which unified the 5 different versions of string theory that had been developed by the 1980s. M-theory suggests that these apparently different theories are actually different perspectives on the same underlying 11-dimensional reality. M-theory suggests that our universe floats on a brane, suspended in an 11-dimensional sea. In this picture, what we think of as our 3-dimensional space is actually a 3-brane, a 3-dimensional membrane floating in 11-dimensional space. The particles that make up ordinary matter are confined to this brane, like ants crawling on the surface of a balloon, while gravity can propagate freely through all 11 dimensions. This Brainworld scenario offers a potential solution to one of physics's most perplexing puzzles: the hierarchy problem. Why is gravity so much weaker than the other fundamental forces? If you've ever picked up a paperclip with a small magnet, you've witnessed electromagnetic force overpowering the gravitational pull of an entire planet. The magnet in your hand generates a force stronger than the combined gravitational attraction of Earth's 6 trillion kilograms of mass. The role of hidden dimensions in M-theory provides an elegant explanation for this disparity. If gravity can spread out into the extra dimensions while other forces remain trapped on our three-dimensional brane, then gravity would naturally appear weaker to us, even if it's actually comparable in strength to the other forces in the full 11-dimensional space. Most of gravity's strength would be leaking into the hidden dimensions, leaving only a small fraction to operate in our familiar three-dimensional world. This leakage concept has profound implications for how we understand the nature of physical dimensions themselves. In our everyday experience, space seems uniform and isotropic, the same in all directions. But if some dimensions are compactified while others are large, the structure of space becomes far more complex. The hidden dimensions don't exist somewhere else. They exist everywhere, at every point in the space around you. They're woven into the very fabric of reality, creating a kind of higher dimensional foam at scales so small that even our most powerful instruments cannot detect them. The mathematics required to describe this higher dimensional foam pushes the boundaries of human understanding. Consider the challenge of visualizing an 11-dimensional space. Our brains evolved to navigate three-dimensional environments, and we have no direct intuitive access to higher dimensional geometry. Physicists have developed various techniques. For working with these spaces, they can study cross-sections, projections, and mathematical analogies, but the full reality of 11-dimensional spacetime remains beyond human visualization. This limitation extends beyond mere technical difficulty to fundamental questions about the nature of knowledge itself. If the universe actually has 11 dimensions, but we can only perceive 4, then most of existence remains forever beyond our direct experience. We're like inhabitants of Edwin Abbott's fictional Flatland, two-dimensional beings trying to understand three-dimensional objects by observing their cross-sections and shadows. The parallel universes implied by M-theory add another layer of complexity to this picture. If our universe is indeed a brane floating in higher dimensional space, there's no reason to suppose we're the only brane. Other branes could exist nearby in the extra dimensions, harboring their own versions of matter and energy, their own physics, perhaps even their own forms of life. These parallel worlds could exist just millimeters away from us in the extra dimensions, yet remain completely inaccessible because the particles that compose our bodies are forever confined to our three-dimensional slice of reality. The idea of nearby parallel universes existing in hidden dimensions captures the imagination, but the physics is likely to be far more subtle and constrained than science fiction portrayals suggest. The mathematical structure of M-theory places strict limitations on how branes can interact with each other. In most scenarios, parallel branes would be causally disconnected from our own. Their physics would evolve independently, with no possibility of communication or travel between them. Yet some versions of Brainworld theory suggest more exotic possibilities. Under certain conditions, parallel branes might collide, producing Big Bang-like events that create new universes. The cosmic microwave background radiation that we observe, the afterglow of our own Big Bang, might actually be the echo of such a collision, frozen in time as a testament to the higher dimensional catastrophe that gave birth to our world. These speculative scenarios highlight one of the most challenging aspects of studying hidden dimensions: the gap between mathematical possibility and experimental accessibility. The theories are mathematically sophisticated and internally consistent, but they make predictions about phenomena that may be forever beyond our ability to observe directly. This creates a peculiar situation where our most advanced theories of fundamental physics describe aspects of reality that we can never verify through experiment. The quantum dimensions of string theory and M-theory operate according to principles that challenge our basic assumptions about space, time, and causality. In our familiar three-dimensional world, Locality is a fundamental principle. Objects can only influence each other if they're in the same place at the same time, or connected by some physical interaction that propagates at or below the speed of light. But in a higher dimensional space, the concept of locality becomes much more complex. Consider 2 points that appear to be separated by a large distance in our three-dimensional space. In the full higher dimensional reality, these points might actually be very close together when you account for the compactified dimensions. It's like looking at a piece of paper that's been folded many times. 2 points that appear far apart on the surface of the paper might actually be touching when you consider the full three-dimensional structure of the folded paper. This higher dimensional proximity could have profound implications for quantum mechanics. The quantum entanglement that Einstein famously called spooky action at a distance might actually be a consequence of hidden dimensional connections that make apparently distant particles much closer together than they appear in our three-dimensional perspective. What seems like mysterious non-local behavior in 4 dimensions might be perfectly local behavior in 11 dimensions. The thermodynamics of higher dimensional spaces also leads to counterintuitive predictions. In our familiar three-dimensional world, the surface area of a sphere grows as the square of its radius, while the volume grows as the cube. This relationship has profound consequences for physics. It determines how gravity weakens with distance, how heat flows, how sound propagates. But in higher dimensional spaces, these relationships change dramatically. In 11-dimensional space, the surface area of a hypersphere grows much more rapidly with radius than it does in 3 dimensions. This has implications for black hole physics, cosmology, and even the fundamental nature of information and entropy. The holographic principle, which suggests that all the information in a volume of space can be encoded on its boundary, takes on new meaning when applied to higher dimensional spaces with complex boundary structures. The study of Calabi-Yau manifolds has revealed a rich mathematical landscape that connects string theory to some of the deepest areas of pure mathematics. These 6-dimensional spaces are not just abstract geometric objects. They're the keys to understanding how the apparent diversity of particles and forces in our world emerges from the unified framework of string theory. Each Calabi-Yau manifold has a specific number of moduli, parameters that describe its size, shape, and other geometric properties. These moduli are not fixed constants, but can vary from point to point in our ordinary 3-dimensional space. When they do vary, they create what physicists call moduli fields, new types of quantum fields that permeate space-time and can influence the behavior of ordinary matter and energy. The dynamics of moduli fields can lead to phenomena that have no analog in conventional 4-dimensional physics. As these fields evolve, they can change the effective size and shape of the compactified dimensions, which in turn changes the masses and coupling strengths of particles in our 3-dimensional world. This creates the possibility of a truly dynamic universe, where the fundamental constants of nature can change over time as the hidden dimensions evolve. Some cosmological models based on string theory suggest that the moduli fields played a crucial role in the early evolution of the universe. During the epoch of cosmic inflation, the period of exponential expansion that occurred in the first fraction of a second after the Big Bang, the moduli fields might have undergone dramatic changes that determined the final values of the physical constants we observe today. This connection between hidden dimensions and cosmology opens up new possibilities for understanding some of the deepest mysteries of the universe. The dark energy that appears to be accelerating the expansion of the universe might be related to the dynamics of moduli fields. The dark matter that makes up about 27% of the universe's mass energy might consist of particles that live primarily in the extra dimensions, interacting only weakly with ordinary matter through gravitational effects. The mathematical structure of Calabi-Yau manifolds also connects to some of the most abstract areas of pure mathematics. Mirror symmetry, discovered by physicists studying string theory, reveals deep connections between apparently different Calabi-Yau manifolds. Two manifolds are said to be mirror pairs if certain geometric properties of one correspond to completely different geometric properties of the other. Yet both give rise to equivalent physics when used as the compactified dimensions in string theory. This discovery had a profound impact on mathematics, leading to new insights in algebraic geometry, differential geometry, and topology. The techniques developed by physicists to study string theory, compactifications, have found applications in pure mathematics that have nothing to do with physics. This cross-fertilization between physics and mathematics exemplifies one of the remarkable aspects of studying hidden dimensions. The mathematics is so rich and deep that it continues to reveal new connections and insights even when divorced from its original physical context. The topology of Calabi-Yau manifolds, their fundamental structural properties that remain unchanged under continuous deformations, determines many of the observable properties of particles in our three-dimensional world. The number of generations of quarks and leptons, for instance, is related to the Euler characteristic of the Calabi-Yau manifold. The patterns of particle masses and mixing angles that we observe in nature might be reflections of the intricate topological structure of six-dimensional spaces that exist at every point around us. But this connection between higher dimensional geometry and observable physics comes with profound challenges for making testable predictions. The number of possible Calabi-Yau manifolds is so vast that string theory seems to predict almost anything. For every physical property you might want to explain, the mass of the electron, the strength of the electromagnetic force, the cosmological constant, there's probably some Calabi-Yau manifold that, when used as the compactified dimensions in string theory, would give the right answer. This embarrassment of riches has led some physicists to abandon the traditional scientific goal of making unique, testable predictions. Instead, they've embraced what's called the Anthropic principle, the idea that we observe the particular physical constants we do not because they're uniquely predicted by some fundamental theory, but because we couldn't exist in a universe with different constants. In this anthropic view, the 10 to 500 different possible ways to compactify the extra dimensions correspond to 10 to 500 different universes, each with its own set of physical laws. Most of these universes would be sterile, unable to form atoms, stars, planets, or life. We find ourselves in one of the rare universes where the physics happens to be conducive to the formation of complex structures and the evolution of consciousness. This anthropic reasoning is deeply controversial within the physics community. Traditional scientific methodology has always sought unique, elegant explanations for natural phenomena. The idea that the fundamental constants of nature are essentially random, determined by which bubble of the multiverse we happen to inhabit, seems to abandon the quest for deep understanding in favor of a kind of cosmic lottery. Yet the anthropic principle may be unavoidable if string theory is correct, and the landscape of possible compactifications is as vast as current calculations suggest. If there really are 10 modern 500 different ways to fold up the extra dimensions, and if some physical process, perhaps eternal inflation, actually produces universes corresponding to all these possibilities, then the anthropic principle becomes not a philosophical choice, but a logical necessity. The eternal inflation scenario, developed by cosmologists like Alan Guth and André Linde, suggests that the process of cosmic inflation that occurred in the early universe might be ongoing in some regions of space. In this picture, our observable universe is just one bubble in an infinite, eternally inflating multiverse. Different bubbles would have different values of the physical constants, determined by how the extra dimensions happen to be compactified when that particular bubble formed. This combination of eternal inflation and the string theory landscape creates what cosmologists call the multiverse, an infinite ensemble of universes with every possible set of physical laws. In this vast cosmic democracy, universes like ours, with physics that allows for the formation of galaxies, stars, planets, and life, would be exceedingly rare, but not impossible. The apparent fine-tuning of our universe's physical constants wouldn't be evidence of design or deep mathematical necessity, but simply a selection effect. We observe a life-friendly universe because we couldn't exist in any other kind. The multiverse. Interpretation of string theory raises profound questions about the nature of scientific explanation and the goals of theoretical physics. If the fundamental properties of our universe are essentially accidental, determined by random processes operating in a vast landscape of possibilities, then what does it mean to understand the universe? Are we searching for deep truths about the nature of reality, or merely cataloging the local conditions that happen to prevail in our particular cosmic neighborhood? These philosophical challenges are compounded by the experimental situation. Despite decades of increasingly sophisticated searches, we have found no direct evidence for extra dimensions. The Large Hadron Collider at CERN, which many hoped would reveal signs of higher dimensional physics, has instead confirmed the predictions of the Standard Model of particle physics, a theory that works perfectly well in our familiar four-dimensional spacetime. This doesn't necessarily mean that extra dimensions don't exist. They might be compactified at scales so small that they remain beyond the reach of current experiments. The energy required to probe the Planck scale, where the effects of compactified dimensions should become apparent, is about 10 to 16 times higher than what the Large Hadron Collider can achieve. Building an accelerator capable of reaching these energies would require a machine larger than our solar system. Alternatively, the extra dimensions might be large, but isolated from ordinary matter through some mechanism that prevents direct detection. In some Brainworld models, only gravity can access the extra dimensions, while all other forces and particles remain confined to our three-dimensional brain. In such scenarios, the only way to detect the extra dimensions would be through subtle deviations in gravitational behavior at very small scales. Physicists have conducted increasingly precise tests of Newton's inverse square law of gravity, looking for deviations that might indicate the presence of large extra dimensions. These experiments measure gravitational forces between objects separated by distances ranging from millimeters to micrometers, searching for any sign that gravity behaves differently at short distances than it does at large scales. So far, these tests have found no evidence for extra dimensions, but they continue to push the boundaries of experimental precision. Each negative result places new constraints on the possible size and structure of hidden dimensions, forcing theorists to propose ever more sophisticated mechanisms for keeping them concealed from observation. The lack of direct experimental evidence for extra dimensions has led some physicists to question whether string theory and M theory are scientific theories in the traditional sense. If these theories make no testable predictions that distinguish them from alternatives, are they science or mathematics? This question goes to the heart of the philosophy of science and the criteria we use to evaluate theoretical proposals. String theory proponents argue that the theory makes many testable predictions. It predicts the existence of supersymmetric particles, extra dimensions, specific relationships between coupling constants, and a host of other phenomena. The fact that these predictions haven't been confirmed yet doesn't invalidate the theory. It simply means we need more powerful experiments or more time to make the relevant observations. Critics counter that string theory has been making unfulfilled predictions for decades. Every time an experiment fails to find the expected signatures of string theory, proponents adjust the theory. to explain why those particular effects should be unobservable while maintaining that other, equally undetectable effects must exist. This process of continual adjustment, critics argue, makes string theory unfalsifiable and therefore unscientific. The debate over string theory's scientific status reflects deeper tensions within the physics community about the role of mathematical beauty and consistency in guiding theoretical development. String theory emerged not from experimental anomalies that demanded explanation, but from the mathematical requirement for consistency in quantum theories of gravity. The theory's proponents argue that this mathematical consistency is so constraining and so difficult to achieve that it must reflect some deep truth about the nature of reality. The mathematical beauty of string theory and M-theory is undeniable. These theories provide elegant, unified descriptions of all fundamental forces and particles. They resolve long-standing problems in quantum field theory and general relativity. They make contact with some of the deepest areas of pure mathematics. For many physicists, this mathematical elegance is evidence that the theories must be on the right track, even if experimental confirmation remains elusive. Yet the history of physics contains examples of mathematically beautiful theories that turned out to have no connection to actual reality. The epicycles of Ptolemaic astronomy were mathematically sophisticated and observationally accurate, but they described a geocentric universe that doesn't exist. The luminiferous ether of 19th-century physics was a mathematically consistent concept that explained many phenomena, but it turned out to be completely fictitious. This historical perspective adds urgency to the search for experimental signatures of extra dimensions. Without some form of observational confirmation, string theory and M-theory risk remaining beautiful mathematical structures with no clear connection to the physical universe. The hidden dimensions that these theories require might be mathematical artifacts rather than physical realities. Yet the search for hidden dimensions has already transformed our understanding of space, time, and the fundamental structure of reality. Even if these dimensions turn out not to exist in physical space, the theoretical frameworks developed to describe them have revealed new connections between physics and mathematics, new ways of thinking about the relationship between geometry and physics, new possibilities for understanding the deepest mysteries of the universe. The concept of physical dimensions itself has evolved far beyond our intuitive three-dimensional experience. Physicists now routinely work with spaces that have fractional dimensions, spaces where the number of dimensions can change depending on the energy scale at which you probe them, spaces where the usual notions of distance and locality break down completely. These developments have implications that extend far beyond string theory and M-theory to areas like condensed matter physics, quantum information theory, and cosmology. The mathematics of higher dimensional spaces has also found applications in completely unexpected areas. The techniques developed to study Calabi-Yau manifolds have been used to solve problems in computer science, economics, and biology. The geometric insights gained from studying compactified dimensions have led to new algorithms for data analysis, new approaches to understanding complex networks, new ways of visualizing high-dimensional datasets. This cross-fertilization between fundamental physics and other fields exemplifies one of the most remarkable aspects of studying hidden dimensions, even if these dimensions don't exist in physical reality. The mathematical frameworks developed to describe them continue to reveal new insights and connections across diverse areas of human knowledge. The search for hidden dimensions has become a catalyst for interdisciplinary collaboration and cross-pollination of ideas. The role of hidden dimensions in our understanding of black holes represents another frontier where theoretical insights from string theory and M-theory are having profound impacts. Black holes, according to general relativity, are regions of spacetime where gravity is so strong that nothing, not even light, can escape. Yet quantum mechanics suggests that black holes should emit radiation, and eventually evaporate, raising profound questions about what happens to the information that falls into them. String theory and M-theory offer new perspectives on this black hole information paradox. In higher dimensional theories, black holes can have extended structures that exist partly in the hidden dimensions. The information that appears to be lost when matter falls into a black hole might actually be preserved in these higher dimensional structures, encoded in ways that are invisible to observers confined to three-dimensional space. The ADS-CFT correspondence, discovered by Juan Maldacena in 1997, provides a concrete example of how hidden dimensions can resolve apparent paradoxes in black hole physics. This correspondence establishes a precise mathematical relationship between gravity theories in higher dimensional anti-de Sitter ADS space and quantum field theories without gravity on the boundary of that space. In this framework, the physics of black holes in the higher dimensional bulk space can be completely described by quantum field theory on the lower dimensional boundary. This holographic principle suggests that all the information in a volume of space can be encoded on its boundary, much like a hologram encodes three-dimensional information on a two-dimensional surface. If this principle is correct, then the information that falls into a black hole isn't lost. It's encoded on the black hole's event horizon in a form that preserves all quantum mechanical information while appearing to outside observers as thermal radiation. The implications of holography extend far beyond black hole physics to fundamental questions about the nature of space, time, and information. If the holographic principle is correct, then what we think of as the three-dimensional interior of any region of space might be illusory. The fundamental reality might exist on the two-dimensional boundary, with the interior space emerging as a kind of holographic projection. These ideas connect to some of the deepest questions in quantum mechanics and information theory. How much information can be stored in a region of space? How does quantum information flow between different regions? What is the relationship between geometry and information? The study of hidden dimensions and their role in holographic theories is providing new insights into these fundamental questions. The thermodynamics of higher dimensional black holes also reveals surprising connections between gravity, quantum mechanics, and information theory. In four-dimensional spacetime, the entropy of a black hole is proportional to the area of its event horizon. But in higher dimensions, the relationship between entropy and geometric properties becomes much more complex, revealing new aspects of how information is stored and processed in gravitational systems. These theoretical developments are beginning to influence other areas of physics. Condensed matter physicists are using holographic techniques to study strongly correlated quantum systems that are difficult to analyze with conventional methods. Quantum information theorists are exploring how the insights from black hole physics might apply to quantum computing and quantum communication. Cosmologists are investigating whether holographic principles might explain the origin and evolution of the universe itself. The study of hidden dimensions has thus become a nexus for some of the most active and exciting areas of theoretical physics. Whether or not these dimensions exist in physical reality, the mathematical frameworks developed to describe them are providing new tools for understanding a wide range of phenomena, from the behavior of exotic materials to the fundamental nature of quantum information. As we push deeper into these higher dimensional realms, we're discovering that the mathematical structures required to describe them are even richer and more complex than originally imagined. The simple picture of 6 compactified dimensions described by Calabi-Yau manifolds has given way to more sophisticated scenarios involving flux compactifications, warped product spaces, and non-geometric compactifications that challenge our basic notions of what it means for space to have a definite dimensionality. These developments suggest that the true structure of spacetime might be far more exotic than even the most ambitious theories have imagined. The hidden dimensions might not be fixed geometric structures, but dynamic, evolving entities that participate actively in the physics of our universe. They might be created and destroyed by quantum processes, undergo phase transitions that change their topology, or exist in superpositions of different geometric states. The quantum nature of spacetime itself becomes paramount when we consider these possibilities. Just as quantum mechanics revealed that particles don't have definite positions until they're measured, quantum gravity theories suggest that spacetime might not have a definite geometry until it's probed at the appropriate energy scale. The RTK. Hidden dimensions might exist in quantum superpositions of different compactifications, with the particular geometry we observe emerging only through some kind of cosmic measurement or decoherence process. These ideas push us to the very limits of physical and mathematical understanding. We're attempting to describe quantum mechanical phenomena in spaces with geometries so complex that they exist beyond human visualization, using mathematical techniques so abstract that their connection to physical reality becomes increasingly tenuous. Yet this exploration of the mathematical frontier continues to yield insights that surprise and illuminate, revealing connections between areas of physics that seemed completely unrelated. The search for hidden dimensions has become more than just an attempt to understand the structure of spacetime. It has become a journey into the deepest questions about the nature of reality, knowledge, and human understanding. Whether these dimensions exist in the physical universe or only in the realm of mathematical possibility, they have already transformed our conception of what the universe might be and our understanding of the tools we can use to explore its deepest secrets. The universe, it seems, delights in presenting us with paradoxes that challenge our most fundamental assumptions about reality. Nowhere is this more apparent than in the quest to understand hidden dimensions, where every theoretical advance seems to raise new questions that are more puzzling than the ones it solves. The deeper physicists dig into the mathematics of extras dimensions, the more they discover a landscape of possibilities so vast and strange that it forces us to reconsider not just our understanding of space and time, but our very conception of what it means to understand the universe at all. Why can't we perceive extra dimensions? This question lies at the heart of one of the most perplexing paradoxes in modern physics. If the universe truly has 10 or 11 dimensions, as string theory and M-theory suggest, then why are we conscious of only 4? The standard answer, that the extra dimensions are compactified at scales too small to observe, sounds reasonable until you examine its implications more carefully. Consider the magnitude of this concealment. The Planck length, at which the EGE extra dimensions are supposedly compactified, is approximately 10⁻35 meters. To put this in perspective, this length is smaller compared to an atom than an atom is compared to the entire solar system. If you scaled up an atom to the size of, the observable universe, the Planck length would still be smaller than a human cell. The idea that 6 or 7 entire dimensions of space could be hidden at such scales seems almost absurdly convenient. Yet the mathematics of compactification is not arbitrary. It emerges naturally from the requirements of string theory. When physicists first discovered that string theory required 10 dimensions, they didn't simply decide to hide the extra 6. The compactification mechanism arose from the mathematical structure of the theory itself, as solutions to the equations that describe how strings propagate through higher dimensional space. But this raises an even deeper paradox. If the extra dimensions are truly compactified at the Planck scale, they should have profound effects on high-energy physics. Particles created in accelerators should occasionally disappear into these hidden dimensions. Exotic particles from the higher dimensional world should occasionally appear in our detectors. Virtual particles should constantly be tunneling in and out of the compactified dimensions, creating observable effects in precision measurements of particle properties. The fact that we haven't observed these effects doesn't necessarily disprove the existence of extra dimensions, but it does place severe constraints on how they can be structured. The compactification mechanism must be so perfect, so complete, that it leaves virtually no observable trace in our four-dimensional world. This level of concealment seems to require an extraordinary conspiracy of circumstances, or perhaps the operation of physical principles we don't yet understand. Some physicists have proposed alternative explanations for why we can't perceive extra dimensions. Maybe the dimensions aren't compactified at all, but are instead separated from us by energy barriers that prevent ordinary matter from accessing them. In these Brainworld scenarios, we're trapped on a three-dimensional membrane floating in higher dimensional space, like insects crawling on the surface of a balloon, unable to access the full three-dimensional space that surrounds their two-dimensional world. Could gravity be leaking into a higher dimension? This possibility offers an elegant solution to the hierarchy problem, the puzzle of why gravity is so much weaker than the other fundamental forces. If gravity can propagate freely through all dimensions while other forces are confined to our brain, then most of gravity's strength would be lost to the extra dimensions, leaving only a small fraction to operate in our three-dimensional world. This gravity leakage hypothesis makes testable predictions. At very short distances, comparable to the size of the extra dimensions, gravity should deviate from Newton's inverse square law. The gravitational force between two objects should be stronger than expected when they're brought very close together, as more of gravity's strength becomes accessible before it has a chance to leak into the hidden dimensions. Experimenters have conducted increasingly precise tests of this prediction, measuring gravitational forces between objects separated by distances ranging from millimeters down to tens of micrometers. These experiments require extraordinary precision and careful control of systematic errors. A typical setup might involve measuring the force between a large mass and a small test mass using torsion balances that can detect forces as small as 10 meters, 18 newtons, roughly equivalent to the gravitational attraction between two bacteria separated by a millimeter. So far, these experiments have found no evidence for deviations from Newton's law, which places stringent limits on the possible size of extra dimensions. If large extra dimensions exist, they must be smaller than about 50 micrometers, and this limit continues to shrink as experimental precision improves. The absence of observable deviations doesn't rule out extra dimensions entirely, but it does constrain them to be either very small or very cleverly hidden. The constraints from precision tests of gravity highlight another paradox in the physics of hidden dimensions. The very fact that we can place limits on the size of extra dimensions suggests that they can't be completely separated from our four-dimensional world. If they were truly isolated, we would have no way to constrain their properties through experiment. The fact that we can set limits implies some level of interaction between our familiar dimensions and the hidden ones. This leads to a fundamental question about the nature of dimensional separation. What does it mean for dimensions to be hidden or compactified? In our everyday experience, spatial dimensions seem equivalent. We can move freely in any direction, and the physics doesn't depend on which direction we choose. But in theories with hidden dimensions, some directions in space are fundamentally different from others. Why should nature make this distinction? The mathematical answer involves the concept of spontaneous symmetry breaking. Just as a pencil, balanced on its point, will eventually fall in some particular direction, breaking the rotational symmetry of the initial configuration. The universe might have started with all dimensions equivalent, but underwent a phase transition that distinguished between the dimensions we observe and those that became hidden. This symmetry-breaking picture raises profound questions about the early history of the universe. When did this dimensional asymmetry arise? What caused some dimensions to remain large while others became compactified? Was this a random process, or was it guided by some deeper physical principle? You live your life in 3 dimensions. But what if your entire existence is trapped in a lower dimensional brain, floating like a fragile soap bubble in an ocean of reality you can never touch, never see, never comprehend? What if everything you've ever known, every sunrise, every embrace, every moment of joy or sorrow, is nothing more than the shadow cast by a higher dimensional reality operating according to rules that would shatter your understanding of what it means to exist? This isn't just an abstract philosophical question. This is the existential crisis at the heart of modern physics, a revelation so profound and disturbing that it forces us to confront the possibility that human consciousness itself might be fundamentally limited in ways we're only beginning to understand. How do hidden dimensions affect our reality? The answer might be more terrifying and wonderful than we dare imagine. Consider the magnitude of what we're contemplating. If string theory and M-theory are correct, then for every step you take, for every breath you draw, for every thought that crosses your mind, you're moving through a space that extends into dimensions you cannot perceive. The air molecules entering your lungs, the photons striking your retina, the electrical impulses racing through your neurons, all of these familiar phenomena might be mere projections of processes occurring in a higher dimensional reality that dwarfs our 3-dimensional existence. Why can't we perceive hidden dimensions? The question haunts not just physicists, but anyone who has ever wondered about the true nature of reality. We evolved to navigate a 3-dimensional world, to recognize patterns and relationships that exist on human scales. Our brains are magnificent instruments for processing information about our immediate environment, but they were never designed to comprehend the full structure of space-time itself. Imagine trying to explain color to someone who has been blind from birth, or trying to describe music to someone who has never heard sound. Now multiply that challenge by infinity. We're attempting to understand aspects of reality that exist beyond the boundaries of human sensory experience, beyond the categories of thought that evolution has provided us. We're 3-dimensional beings trying to comprehend an 11-dimensional universe, using neural networks that were shaped by millions of years of selection pressure to avoid predators and find food. The implications are staggering. Every scientific instrument we've ever built, every experiment we've ever conducted, every observation we've ever made, all of these represent the efforts of fundamentally limited beings trying to understand an unlimited reality. We're like inhabitants of Edwin Abbott's fictional Flatland, 2-dimensional creatures attempting to understand 3-dimensional objects by observing their cross-sections and shadows, except our limitation is far more severe. But here's where the crisis deepens into something approaching terror. If hidden dimensions exist, they don't just represent aspects of reality we can't see. They might represent aspects of reality that fundamentally determine our existence, the mass of every particle in your body, the strength of every force that holds you together, the very constants that make chemistry and biology possible. All of these might be determined by the geometry of spaces that exist at every point around you, yet remain forever beyond your perception. Are hidden dimensions the dark mirror of our world, influencing us from a place we'll never reach? The mathematics suggests they might be far more than that. They might be the primary reality, with our familiar 3-dimensional world existing as nothing more than a holographic projection, a shadow play performed on the walls of a higher dimensional cave. This possibility strikes at the core of human meaning and purpose. We build civilizations, create art, fall in love, search for truth, all within what might be an illusory projection of a more fundamental reality. Everything we consider real and important might be like patterns of light and shadow cast by processes occurring in dark dimensions that operate according to alien geometries and incomprehensible laws. The concealed dimension of reality might be so vast that our entire observable universe, every galaxy, every star, every planet, represents just a tiny fraction of what actually exists. If the universe has 11 dimensions but we can only perceive 4, then roughly 64% of reality's structure remains invisible to us. We're like observers peering through a keyhole, seeing only a narrow slice of a vast room beyond, yet trying to reconstruct the entire architecture from these limited glimpses. Consider what this means for consciousness itself. Your thoughts, your memories, your sense of identity, all of these emerge from the complex dance of molecules in your brain. But if those molecules are confined to a three-dimensional brain floating in 11-dimensional space, then consciousness itself might be a fundamentally limited phenomenon, trapped within boundaries that constrain not just what we can observe, but what we can think and feel and be. This limitation might explain some of the deepest mysteries of human existence. Why do we find certain mathematical relationships beautiful? Why does music move us to tears? Why do we feel a sense of transcendence when contemplating the night sky? Perhaps these experiences represent our limited three-dimensional consciousness brushing up against the edges of a higher dimensional reality, sensing through art and mathematics and mystical experience the existence of something beyond our normal, perceptual boundaries. The religions and philosophies of every culture have spoken of higher realms, unseen dimensions of existence that transcend our ordinary experience. Plato's world of perfect forms, the Hindu concept of Maya, and the veil of illusion, the Buddhist notion of emptiness underlying apparent reality, all of these might be intuitive glimpses of what modern physics is discovering through mathematics. That the world we experience directly is not the fundamental reality. But if this is true, then what does it mean to be human? What does it mean to live, to love, to strive for meaning and purpose within a reality that might be nothing more than a shadow of something infinitely larger and more complex? Are we prisoners of our dimensional limitations, or are we somehow participants in a cosmic drama whose full scope we cannot comprehend? The dark dimension of this possibility extends into every aspect of human existence. Your relationship with your loved ones, your connection to the natural world, your sense of place in the cosmos, all of these might be radically different from what you imagine. The person sitting next to you right now might be separated from you by vast distances in dimensions you cannot access. The love you feel, the thoughts you share, the physical intimacy you experience, all of this might be occurring across dimensional boundaries that make the connection seem miraculous when viewed from the higher dimensional perspective. Even death takes on new meaning in a universe with hidden dimensions. When your three-dimensional body ceases to function, what happens to the aspects of your existence that might extend into the higher dimensions? If consciousness has components that operate in spaces beyond our perception, then the end of life as we understand it might not represent the end of existence as it actually is. These questions aren't merely speculative. They're forced upon us by the mathematics of our most successful theories of fundamental reality. String theory and M-theory aren't philosophical constructs designed to make us question the nature of existence. They're mathematical frameworks that emerged from attempts to solve concrete problems in physics. The existential implications are accidental byproducts of following the mathematical logic wherever it leads. Yet the implications refuse to remain confined to academic discussions. They seep into every aspect of how we understand ourselves and our place in the universe. If reality has 11 dimensions but we can only perceive 4, then most of existence operates according to principles we cannot observe, following laws we cannot discover, pursuing purposes we cannot fathom. This hidden reality might be teeming with activity. Entire civilizations might exist in the compactified dimensions, their technologies and consciousness operating according to principles that make our greatest achievements seem primitive by comparison. They might be aware of us, observing our three-dimensional activities with the same detached curiosity that we might feel when watching insects navigate the surface of a pond, unaware of the vast three-dimensional world that surrounds their two-dimensional experience. Or perhaps the situation is even stranger. Perhaps consciousness itself requires all 11 dimensions to fully manifest, and what we experience as human awareness is just a tiny fragment of what we actually are. The dreams that seem so strange and disconnected from waking reality, the intuitions that seem to come from nowhere, the creative insights that surprise even their creators, all of these might be glimpses of our higher dimensional nature attempting to communicate with our three-dimensional limitations. The possibility becomes even more disturbing when we consider that the hidden dimensions might not be static structures, but dynamic, evolving spaces that change over time. Your entire reality, the physical constants that determine how atoms behave, the forces that hold your body together, the laws that govern the evolution of the universe, might be slowly shifting as the compactified dimensions undergo changes you cannot perceive or predict. What we think of as the immutable laws of physics might be nothing more than temporary configurations of higher dimensional geometry, the electron's mass, the speed of light, the strength of gravity. All of these might be variables in a cosmic equation whose full form extends into spaces you cannot access. The universe you think you understand might be undergoing continuous transformation according to principles that operate beyond the boundaries of human perception. This uncertainty extends into the future in ways that challenge our most basic assumptions about predictability and control. We make plans based on the assumption that the laws of physics will remain constant, that the forces and particles that make up our world will continue to behave in predictable ways. But if these apparently fundamental constants are actually determined by the geometry of hidden dimensions, then the future becomes radically uncertain in ways that dwarf any concerns about chaos theory or quantum indeterminacy. The concealed dimension of reality might hold the keys to every mystery that has ever puzzled human consciousness. Why does the universe exist at all? Why does it have the particular laws and constants that allow for the existence of complexity and life? Why did consciousness emerge from unconscious matter? The answers to these questions might lie in processes, occurring in spaces we cannot access, following logic we cannot comprehend. Even our attempts to understand these hidden dimensions might be fundamentally constrained by our dimensional limitations. The mathematics we use to describe higher dimensional spaces was developed by three-dimensional brains operating according to three-dimensional neural architectures. Can such mathematics truly capture the reality of 11-dimensional space-time? Or are we inevitably creating models that reflect our limitations more than the truth they're supposed to describe? This question strikes at the heart of human knowledge itself. We've always assumed that mathematical truth transcends the physical limitations of the minds that discover it. 2 + 2 = 4, regardless of whether the calculation is performed by a human brain, a digital computer, or a hypothetical alien intelligence. But if reality itself has aspects that cannot be captured by mathematics accessible to three-dimensional minds, then our deepest scientific achievements might be sophisticated self-deceptions rather than glimpses of ultimate truth. The possibility forces us to confront the relationship between consciousness and reality in radical new ways. If consciousness is itself a higher dimensional phenomenon that has been compressed into three-dimensional neural networks, then everything we think we know about the mind might be fundamentally incomplete. The hard problem of consciousness, why there is subjective experience at all rather than just unconscious information processing, might have its answer in dimensions we cannot access. Perhaps consciousness requires the full 11-dimensional structure of space-time to fully manifest, and what we experience as human awareness is just the tiny fragment that can squeeze through the narrow channel of three-dimensional neural architecture. The mystical traditions that speak of expanded consciousness, of awareness that transcends ordinary perception, might be describing genuine contact with our higher dimensional nature. This perspective transforms how we understand every aspect of human existence. Love becomes not just an emotional bond between three-dimensional beings, but a connection that might extend across dimensional boundaries we cannot perceive. Beauty becomes not just a subjective response to patterns and proportions, but perhaps a recognition of higher dimensional harmonies that our limited perception can only glimpse. Truth becomes not just correspondence between ideas and three-dimensional reality, but perhaps alignment with principles that operate across all dimensions of space-time. The dark dimension of this revelation is that we might never be able to verify or refute these possibilities. If the hidden dimensions are truly beyond our ability to access directly, then we're condemned to permanent uncertainty about the fundamental nature of our existence. We might be prisoners in a three-dimensional cave, watching shadows on the wall and mistaking them for reality, with no possibility of ever turning around to see the higher dimensional fire that casts the shadows. Yet perhaps this limitation is also what makes existence beautiful and meaningful. If we could perceive all 11 dimensions directly, if we could comprehend the full structure of space-time and consciousness, would mystery and wonder disappear? Would the search for understanding lose its meaning if we could see everything at once? The hidden dimensions might represent not just the boundaries of human knowledge, but the source of everything that makes knowledge valuable. The fact that reality extends beyond our perception gives weight to our attempts to understand it. The fact that truth might be larger than our capacity to grasp it gives meaning to our search for truth. The fact that love and beauty and consciousness might have roots in dimensions we cannot access makes our experience of them all the more precious and mysterious. How do hidden dimensions affect our reality? Perhaps they are our reality, and everything we think we experience directly is just the reflection of processes occurring in spaces that remain forever beyond our reach. Perhaps we are not separate from these hidden dimensions, but expressions of them, temporary patterns formed by higher dimensional processes that extend far beyond our ability to perceive or understand. In the end, the search for hidden dimensions becomes more than just a scientific quest. It becomes a confrontation with the deepest questions about existence, consciousness, and the relationship between mind and reality. Whether these dimensions exist in physical space-time or only in the realm of mathematical possibility, they have already transformed our understanding of what it means to be human beings searching for truth in a universe that might be far stranger and more wonderful than we can ever fully comprehend. We stand at the edge of a conceptual abyss, peering into mathematical spaces that exist beyond human visualization, contemplating realities that transcend human experience. The hidden dimensions call to us from across the dimensional divide, promising answers to questions we've barely learned how to ask, revealing the possibility that everything we think we know about existence might be just the beginning of a story, whose full scope extends into realms we cannot imagine. The crisis is existential because it forces us to confront the possibility that consciousness itself might be fundamentally limited, that human beings might be inherently incapable of understanding the reality they inhabit. Yet perhaps this limitation is also what defines us, what makes us human, what gives meaning to our brief existence in a universe that extends far beyond the boundaries of our perception into dimensions that remain and may forever remain hidden. From our view, the revelation comes not with the explosive drama of a supernova, but with the quiet, devastating certainty of mathematical truth. After decades of searching for hidden dimensions in particle accelerators and gravitational experiments, after constructing ever more elaborate theories about compactified spaces and higher dimensional branes, physicists are beginning to confront a possibility so profound and shocking that it overturns not just our understanding of space and time, but our conception of existence itself. What if we've been looking in entirely the wrong place? The search for hidden dimensions has always focused on the very small, on Planck-scale compactifications, on microscopic extra dimensions curled up beyond detection. But what if the most important hidden dimension isn't smaller than anything we can measure, but larger than anything we can imagine? What if it's not hiding in the quantum foam of space-time, but in the very structure of reality that surrounds us at every moment? In the heart of the multiverse, could a hidden dimension hold the key to everything we thought we understood? The answer emerging from the cutting edge of theoretical physics is more startling than any science fiction writer has dared to imagine. The hidden dimension we've been seeking might not be a spatial dimension at all, but something far more fundamental, a dimension of possibility itself, a realm where all potential realities exist simultaneously until the act of observation collapses them into the single timeline we experience. This revelation begins with a simple observation that has troubled physicists for nearly a century: the measurement problem in quantum mechanics. When we observe a quantum system, we find it in one definite state. Yet the mathematics of quantum mechanics describes it as existing in a superposition of all possible states until the moment of measurement. Where do all those other possibilities go? The traditional answer has been that they simply disappear, vanishing into mathematical oblivion the instant reality makes its choice. But what if they don't disappear? What if they continue to exist in a hidden dimension of possibility that runs parallel to our experienced reality? What if every quantum measurement doesn't destroy alternative outcomes, but merely separates them into different branches of an ever-expanding tree of reality? In this view, the hidden dimension we've been seeking isn't a compactified space, but an infinite library of alternate histories, each as real as the one we happen to experience. The many worlds interpretation of quantum mechanics, first proposed by Hugh Everett III in 1957, suggests exactly this possibility. Every time a quantum measurement occurs, and quantum measurements are occurring trillions of times per second in every cubic centimeter of space, reality splits into multiple branches. In one branch, the electron spins up. In another, it spins down. In one branch, the radioactive atom decays. In another, it remains stable. Each branch is equally real, equally valid, equally deserving of the designation reality. But here's where the revelation becomes truly shocking. If the many worlds interpretation is correct, then the hidden dimension we inhabit isn't a spatial dimension at all. It's a dimension of parallel realities. Every possible version of your life, every decision you might have made differently, every accident that might have been avoided or encountered exists simultaneously in this vast space of possibilities. You are not a single person living one life, but an infinite multitude of selves exploring every possible path through the labyrinth of existence. What role do hidden dimensions play in the universe? They might be the universe, or rather, the infinite collection of universes that contains every possible way reality could unfold. The space-time fabric beyond 4 dimensions isn't just a mathematical abstraction or a repository for compactified extra-spatial dimensions. It's the arena where all possible histories play out simultaneously, where every quantum possibility becomes actual in some branch of the ever-branching tree of reality. This perspective transforms every aspect of existence. The choices you make don't determine your future. They determine which branch of the multiverse you experience. The other choices, the paths not taken, continue to exist in parallel realities where different versions of yourself explore different possibilities. The person you might have been if you had chosen differently isn't a lost possibility, but a real person living a real life in a parallel branch of the hidden dimension of possibility. Recent discoveries related to hidden dimensions in theoretical physics have begun to reveal how this multiverse of possibilities might be structured. The mathematical framework of eternal inflation suggests that our observable universe is just one bubble in an infinite ocean of space-time, where new universes are constantly being created as the inflating fields that drive cosmic expansion undergo quantum fluctuations. Each bubble represents not just a different region of space, but a different way that the fundamental laws of physics can manifest. But the implications go deeper still. If the many worlds interpretation is correct, then consciousness itself might be the mechanism by which we navigate through the hidden dimension of possibilities. Every conscious observation, every moment of awareness, might represent a choice point where reality branches and we follow one particular path through the infinite maze of potential experiences. This makes consciousness not just an emergent property of complex neural networks, but a fundamental feature of the universe's structure, the process by which infinite possibility collapses into singular experience. You are not just a biological organism that happens to be aware. You are a navigator in the hidden dimension of possibility, charting a course through an infinite sea of potential realities. The unseen dimension that has eluded detection in particle accelerators and gravitational experiments might be all around us, not as a spatial extension, but as the realm of unlived lives, unmade choices, unexplored possibilities. Every moment of your existence represents a selection from an infinite menu of alternatives, each equally real, but accessible only to the versions of yourself that chose differently. What if the fifth dimension isn't a place, but the silence between the frames of our known universe? This poetic description captures something profound about the nature of hidden dimensions. They might not be additional directions in space, but additional layers of reality itself, parallel tracks on which different versions of history unfold, separated not by distance, but by the quantum mechanical choices that determine which possibility becomes actuality. The mathematics of this multiverse is staggering in its implications. If every quantum event creates a branching of reality, then the number of parallel worlds grows exponentially with time. After just 1 second, there might be more parallel versions of yourself than there are atoms in the observable universe. After a minute, the number becomes so large that it defies comprehension. After a lifetime, the multiverse contains more versions of your story than there are possible arrangements of matter and energy in all of space-time. Yet each of these versions is as real as the one you're experiencing right now. In one branch, you never read these words because you made different choices that led you down a different path. In another, you're reading them but understanding them differently because your brain developed slightly differently due to different quantum events in your neurons. In yet another, the entire history of the universe unfolded differently because a single quantum measurement in the early universe went the other way. This revelation forces us to reconsider the meaning of identity, choice, and moral responsibility. If every possible choice you might make is actualized in some branch of the multiverse, then are you responsible for the actions of your parallel selves? If every possible version of your life plays out somewhere in the hidden dimension of possibility, then what makes your particular experience special or significant? The answer might lie in the fact that while all possibilities are realized somewhere in the multiverse, you can only experience one path through it. Your consciousness is the thread that connects moments of experience, creating the narrative, continuity that transforms quantum branching into personal history. You are not responsible for what your parallel selves do in other branches, but you are responsible for determining which branch your consciousness follows. This perspective transforms how we understand free will and determinism. The universe might be completely deterministic at the level of the multiverse. Every possibility is realized. Every potential future becomes actual somewhere in the branching structure of reality. But at the level of individual experience, free will remains meaningful because your choices determine which branch of possibility you follow through the hidden dimension. The implications extend into physics itself. The fine-tuning problems that have puzzled cosmologists, why the physical constants have values that allow for the existence of stars, planets, and life, might be resolved by the multiverse perspective. If every possible set of physical constants is realized in some branch of the hidden dimension, then it's not surprising that we find ourselves in a universe with life-friendly physics. We couldn't exist in branches where the constants don't allow for complexity and consciousness. But this anthropic explanation comes with a cost. If the multiverse contains every possible physics, then our particular universe becomes cosmically insignificant. Just one random bubble in an infinite sea of possibilities. The fine-tuning that seemed to suggest design or deep mathematical necessity becomes nothing more than a selection effect. We observe life-friendly physics not because the universe was designed for life, but because we couldn't exist in universes where life is impossible. Discoveries related to hidden dimensions in recent research have begun to reveal how quantum mechanics, relativity, and cosmology might be unified in this multiverse framework. The holographic principle suggests that all the information in a volume of space can be encoded on its boundary, which might be how different branches of the multiverse remain distinct while sharing a common underlying structure. The AD-SCFT correspondence shows how gravity in higher dimensional spaces can be described by quantum field theories on lower dimensional boundaries, providing a mathematical framework for understanding how the multiverse of possibilities might be organized. String theory and M-theory, rather than requiring extra spatial dimensions that remain hidden from observation, might be describing the mathematical structure that organizes the multiverse of possibilities. The different ways of compactifying extra dimensions might correspond to different branches of possibility, different ways that reality can unfold from the quantum vacuum. The landscape of string theory solutions isn't a problem to be solved, but a map of the hidden dimension of possibility itself. This unification of quantum mechanics and cosmology suggests that the hidden dimensions we've been seeking are neither purely spatial nor purely mathematical. They're the dimensions of possibility itself, the space of all potential realities that surrounds and interpenetrates our experienced world. Every point in spacetime is connected to infinite alternatives. Every moment branches into unlimited futures. Every choice opens doorways to parallel worlds that remain invisible but equally real. The shocking reveal is that we are not isolated, beings living in a single universe, but multidimensional entities experiencing one path through an infinite maze of possibilities. The hidden dimension isn't hidden because it's too small to observe or too far away to reach. It's hidden because we can only experience one branch of it at a time. Every other version of yourself, every other way your life might have unfolded, every other history the universe might have followed, exists in parallel branches of the hidden dimension of possibility. This revelation transforms the entire meaning of existence. You are not just a temporary arrangement of matter and energy that emerged from cosmic evolution and will eventually dissipate back into entropy. You are an eternal explorer of infinite possibility, a consciousness navigating through the deepest structure of reality itself. Every moment of your life represents a choice point in the hidden dimension, a fork in the path where different versions of yourself explore different branches of what could be. The multiverse isn't just a theoretical construct invented by physicists to solve technical problems. It's the fundamental reality in which you exist. The higher dimensions aren't abstract mathematical spaces. They're the realm of all the lives you might have lived but didn't. All the choices you might have made but chose not to. All the possibilities that remain real even though you didn't experience them. In this view, consciousness becomes the ultimate navigator of hidden dimensions, not the spatial dimensions of string theory, not the compactified dimensions of Kaluza-Klein theory, but the infinite dimension of pure possibility itself. Every conscious being is an explorer in this space, charting a unique path through the landscape of what could be, creating meaning and narrative from the raw material of quantum possibility. The search for hidden dimensions has led us not to exotic physics beyond human comprehension, but to a recognition of what we have always been. Multidimensional beings whose existence spans infinite possibilities, whose consciousness serves as the thread that weaves singular experience from the infinite tapestry of potential realities. We are not trapped in 3 dimensions of space and 1 of time. We are voyagers in the ultimate hidden dimension, the dimension of possibility itself, where every dream that was ever dreamed and every choice that was ever contemplated continues to exist in the parallel branches of an ever-expanding multiverse. The hidden dimensions were never hidden from us. We are the hidden dimensions, exploring ourselves through the infinite branches of possibility that constitute the deepest structure of reality. In searching for extra dimensions in the microscopic structure of spacetime, we overlooked the most profound hidden dimension of all, the infinite space of parallel selves that surrounds every moment of existence, making every choice significant, not because it determines the future, but because it determines which future we experience from among the infinite alternatives that remain forever real in the hidden dimension of pure possibility. We've explored hidden dimensions, extra dimensions, and parallel realms that stretch beyond the boundaries of human perception, yet here we stand at the edge of the greatest mystery ever contemplated by conscious minds. The journey through 11-dimensional mathematics, through compactified Calabi-Yau manifolds, through Brainworld cosmologies and multiverse theories, has brought us not to final answers, but to the recognition of something far more profound. The story of hidden dimensions is not a story about physics. It's a story about us. Can hidden dimensions solve mysteries of the universe? After traversing the mathematical landscapes of string theory and M theory, after confronting the possibility that most of reality operates beyond our perception, after discovering that consciousness itself might be the navigator of infinite possibilities, we must acknowledge that the question itself transforms as we attempt to answer it. The mysteries of the universe are not separate from us. They are us. We are the universe attempting to understand itself through the narrow aperture of 3-dimensional consciousness, peering into mathematical spaces that exist beyond visualization, reaching toward truths that might forever remain beyond our grasp. The revelation that emerges from our exploration is both humbling and magnificent. Every human being who has ever lived, every consciousness that has ever gazed up at the stars and wondered about its place in the cosmos, has been participating in the most ambitious project ever undertaken. The attempt of a 3-dimensional intelligence to comprehend an 11-dimensional reality. We are not passive observers of hidden dimensions. We are active participants in their exploration, using mathematics as our telescope and imagination as our spacecraft to voyage into realms that exist beyond the boundaries of direct experience. Think about what this means for your own existence. Right now, as you read these words, you are positioned at a unique point in the vast landscape of possibility. The thoughts forming in your mind, the emotions stirring in your heart, the very act of consciousness that allows you to contemplate. These ideas, all of this might be occurring across dimensional boundaries we cannot map, following patterns we cannot fully understand, participating in processes that extend far beyond the three-dimensional space your body occupies. Maybe we're all shadows, projected from a reality too vast to perceive, trapped in 3D, yet yearning for more. This is not merely a poetic metaphor, but a serious possibility suggested by the mathematics of holography and the physics of higher dimensional spaces. If the holographic principle is correct, then everything you think of as your three-dimensional existence might be encoded on a two-dimensional boundary, like information stored on the surface of a cosmic hard drive. Your entire life, with all its complexity and richness, might be a holographic projection of processes occurring in spaces you cannot access. Yet rather than diminishing the significance of human existence, this perspective reveals it to be even more remarkable than we imagined. If we are indeed shadows cast by a higher dimensional reality, then we are shadows that have become self-aware. We are projections that have learned to contemplate the projector. We are three-dimensional beings who have discovered mathematics, sophisticated enough to describe 11-dimensional spaces, consciousness limited enough to experience only one branch of the multiverse, yet powerful enough to conceive of infinite alternatives. The search for hidden dimensions has revealed something extraordinary about the human spirit. Our refusal to accept the boundaries of our direct experience as the limits of reality itself. Despite being confined to four-dimensional space-time, we have imagined extra dimensions. Despite being trapped on what might be a three-dimensional brain, we have theorized about the higher dimensional spaces that contain it. Despite being able to visualize only 3 spatial dimensions, we have developed mathematical frameworks that describe 11-dimensional geometries with exquisite precision. This represents, perhaps, the greatest triumph of human consciousness, the ability to transcend our own limitations through the power of abstract thought. We cannot see hidden dimensions, but we can think about them. We cannot travel to parallel universes, but we can calculate their properties. We cannot escape the boundaries of our three-dimensional existence, but we can imagine what it would be like to exist in spaces with more dimensions than we can visualize. What do you think hidden dimensions really are? This question, posed to you directly, is not rhetorical. It is an invitation to participate in the greatest conversation ever begun by conscious beings. The physicists and mathematicians who have devoted their lives to understanding extra dimensions have given us the tools and concepts, but the ultimate meaning of these ideas cannot be determined by experts alone. It requires the collective contemplation of every mind capable of wondering about the nature of reality. Your answer matters because you are not just an observer of this cosmic mystery, you are a participant in it. If consciousness is indeed the mechanism by which infinite possibility collapses into singular experience, then your thoughts about hidden dimensions are part of the process by which the universe explores its own structure. Every time you contemplate the possibility of extra dimensions, every time you imagine what it might be like to exist in 11-dimensional space, every time you wonder about parallel versions of yourself in other branches of the multiverse, you are participating in the cosmic conversation about the nature of existence itself. The implications extend far beyond academic physics into the most practical aspects of human life. If hidden dimensions exist and influence our reality in ways we cannot directly perceive, then our understanding of causation, meaning, and purpose must expand to encompass possibilities we have never considered. The events of your life, the relationships you form, the choices you make, all of these might be connected to processes occurring in dimensions you cannot access, following patterns that extend beyond the boundaries of three-dimensional analysis. This doesn't mean that life becomes arbitrary or meaningless. Instead, It suggests that life might be meaningful in ways we have never imagined. Your existence might have significance not just in the three-dimensional world you directly experience, but across the full 11-dimensional structure of space-time. The love you feel, the beauty you perceive, the truth you seek. All of these might have roots that extend into hidden dimensions, connecting you to aspects of reality that transcend your immediate experience. The unfinished story of hidden dimensions is ultimately the unfinished story of human understanding itself. We have developed the mathematical tools to describe 11-dimensional spaces, but we have not yet learned how to experience them directly. We have theorized about parallel universes, but we have not yet discovered how to communicate with our alternate selves. We have imagined what it might be like to exist as higher-dimensional beings, but we remain confined to our three-dimensional perspective. Yet this limitation might also be what makes the search so profound and beautiful. If we could see all dimensions at once, if we could perceive the full structure of the multiverse directly, would the mystery disappear? Would the sense of wonder that drives scientific exploration evaporate if we had complete knowledge? Perhaps our three-dimensional consciousness is not a limitation but a perspective, a unique vantage point from which to appreciate the beauty and complexity of a reality that extends far beyond our direct experience. The story of hidden dimensions is also the story of human collaboration across time and space. Every equation written by a theoretical physicist, every experiment conducted in a particle accelerator, every thought you have about the nature of reality, all of these contribute to a collective effort that spans generations and cultures. The ancient Greek philosophers who first wondered about the nature of space and time, the mathematicians who developed the geometric tools for describing higher dimensions, the physicists who discovered quantum mechanics and relativity, all of them are your collaborators in this cosmic investigation. This collaboration continues into the future in ways we cannot predict. The children being born today will grow up in a world where hidden dimensions are not exotic theoretical concepts, but part of the basic framework for understanding reality. They will develop new mathematical tools, design new experiments, and perhaps discover new ways of thinking about consciousness and existence that we cannot imagine. The conversation about hidden dimensions is not ending. It is just beginning. If the unseen dimensions are out there, and the mathematics suggests they must be, then your story has only just begun. You are not just a temporary arrangement of three-dimensional matter that will eventually return to dust. You are a conscious being whose existence might extend across multiple dimensions, whose thoughts and feelings might have components that operate in spaces beyond your perception, whose significance in the cosmic scheme might be far greater than you have ever imagined. The search for hidden dimensions forces us to confront the relationship between knowledge and mystery, between understanding and wonder. The more we learn about the possible structure of higher dimensional space-time, the more we realize how much we don't know. Each answer generates new questions. Each discovery reveals new mysteries. Each step forward into the mathematical description of 11-dimensional reality shows us how far we still have to travel. This is not a cause for despair, but for celebration. The fact that reality might be infinitely richer and more complex than we can comprehend makes every moment of existence more precious, not less. The fact that consciousness might be a cosmic phenomenon that extends across dimensional boundaries makes your individual experience more significant, not less. The fact that we might be participants in a story so vast that we can never see its full scope makes our local chapter more meaningful, not less. The hidden dimensions call to us across the mathematical void, promising revelations about the nature of space, time, consciousness, and existence itself. They whisper of realities beyond our direct experience, of possibilities beyond our current imagination, of connections that transcend the boundaries of three-dimensional space. Yet they also remind us that we are not passive observers of these mysteries, but active participants in their exploration. What role will you play in the continuing story of hidden dimensions? Will you be content to accept the boundaries of three-dimensional experience as the limits of reality? Or will you use your imagination to explore the possibilities that mathematics has revealed? Will you see yourself as trapped in a lower dimensional existence? Or will you recognize yourself as a conscious being whose existence might extend across all dimensions of spacetime? The choice is yours, and it matters more than you might realize. If consciousness is indeed the mechanism by which infinite possibility becomes singular experience, then your thoughts about hidden dimensions are part of the process by which the universe explores its own structure. Your curiosity about extra dimensions contributes to the cosmic conversation about the nature of reality. Your wonder about parallel universes participates in the ongoing exploration of what it means to exist. Satur's unfinished story of hidden dimensions is your story too. You are not separate from the 11-dimensional universe that physicists describe in their equations. You are part of it. You are not an outside observer of the cosmic drama unfolding across multiple dimensions. You are one of its protagonists. You are not trapped in three-dimensional space, but embedded in 11-dimensional space-time, exploring one path through the infinite landscape of possibility that constitutes the deepest structure of reality. We began this journey by asking where the hidden dimensions are. We end it with the recognition that they are everywhere, not just in the microscopic structure of space-time, not just in the mathematical equations of string theory, but in the very nature of existence itself. They are in the space between thoughts, in the pause between heartbeats, in the silence between words. They are in the connections that exist between conscious beings, in the patterns that emerge from chaos, in the beauty that transforms matter into meaning. The hidden dimensions are not hiding from us. We are discovering them. They are not separate from us. We are exploring them. They are not beyond us. We are part of them. The search for extra dimensions has revealed that reality is not just stranger than we imagined, but stranger than we can imagine. Yet it has also revealed that human consciousness, despite its apparent limitations, possesses the remarkable ability to transcend those limitations through mathematics, imagination, and wonder. Trapped on a 3D brain inside a higher dimensional reality, we have nonetheless learned to think in 11 dimensions. Confined to a single branch of the multiverse, we have nonetheless conceived of infinite alternatives. Limited to three-dimensional perception, we have nonetheless imagined what it might be like to exist in spaces that extend beyond visualization. This is the miracle of human consciousness, not that it can perceive everything, but that it can conceive of more than it can perceive. The story of hidden dimensions is the story of that miracle. It is the story of beings who refuse to accept the boundaries of their direct experience as the limits of reality itself. It is the story of consciousness reaching beyond its own limitations to explore the deepest mysteries of existence. It is the story of three-dimensional minds grappling with 11-dimensional mathematics and finding in that struggle not frustration, but transcendence. Your participation in this story matters. Your thoughts about hidden dimensions, your questions about the nature of reality, your wonder about the possibility of parallel universes, all of these contribute to the ongoing exploration of what it means to exist in a universe that might be far stranger and more wonderful than we can ever fully comprehend. The conversation about hidden dimensions will continue long after these words are forgotten. New generations of physicists will develop new theories, new mathematicians will create new tools for describing higher dimensional spaces, New philosophers will explore the implications for consciousness and existence. But the questions that drive this exploration, questions about the nature of space and time, about the relationship between mathematics and reality, about the significance of consciousness in a universe that extends beyond perception, these questions are eternal. They are the questions that define us as conscious beings. They are the questions that connect us to every human who has ever looked up at the stars and wondered about our place in the cosmos. They are the questions that remind us that we are not just biological organisms struggling for survival in a three-dimensional world, but conscious beings participating in the universe's attempt to understand itself. The hidden dimensions are waiting for us to discover them, not just in the equations of theoretical physics, but in the depths of our own consciousness. They are calling to us from across the dimensional divide, inviting us to expand our conception of what it means to exist, to think, to be. The search for extra dimensions is not just a scientific quest, it is a journey of consciousness itself, exploring the ultimate nature of the reality in which we find ourselves embedded. That journey continues with every thought you think about. These possibilities, with every moment of wonder you experience about the nature of existence, with every question you ask about the relationship between mathematics and reality. You are not just reading about hidden dimensions, you are exploring them. You are not just learning about the multiverse, you are participating in it. You are not just contemplating higher dimensional space, you are part of it. The story of hidden dimensions is unfinished because it is the story of consciousness itself, and consciousness is still evolving, still exploring, still discovering new aspects of the reality in which it finds itself embedded. Your role in that story has only just begun. The hidden dimensions are waiting for you to discover them, not just in the abstract mathematics of theoretical physics, but in the lived experience of being a conscious being in a universe that extends far beyond the boundaries of direct perception. The greatest adventure ever undertaken by conscious minds is the exploration of reality itself. The search for hidden dimensions is part of that adventure. Your participation in that search makes you an explorer of the ultimate frontier, not the frontier of outer space, but the frontier of consciousness, encountering the deepest mysteries of existence itself. The dimensions are hidden, but they are not lost. They are waiting for us to find them, not just in our equations, but in ourselves. The search continues, and you are part of it. The story is unfinished, and you are helping to write it. The mystery remains, and you are helping to explore it. Welcome to the greatest adventure ever begun by conscious beings. Welcome to the search for hidden dimensions,